My name is Robert DeMarco. I'm a systems and software engineer at Lockheed Martin. I'm doing my master's degree at North Carolina State in electrical and computer engineering.
And my name is Matt Benbow. I'm an electrical engineer, and this is my final semester of the same master's program.
We're showing you here our work on transformer nameplate identification for arc flash analysis using convolutional neural networks.
Here we'll go over an overview of our problem, the input data that was provided to us, the structure of our model, our hyperparameter tuning methods, and our final test results.
So now I'll talk about our problem overview. So currently at work, I'm working on a large arc flash project. Arc flash is when a short circuit occurs on an electrical system, and it produces so much energy that it can vaporize metal and essentially cause an explosion, which can damage and hurt electricians and can be fatal. The first step of this arc flash analysis is to catalog all electrical equipment in the field, and since there are thousands of wells and facilities and hundreds of thousands of images to categorize, it takes a lot of time. So this neural network will increase productivity by being able to automatically sort out which images we need and we don't need. The data for this neural network project is real-world industry data that is provided by my work. The dataset contains 11,830 colored images that have been downsampled to 100 by 100 pixels to protect the company information. 11,085 of these images are non-transformer nameplates, for example the top 5 images shown here. 745 of the images are transformer nameplates, for example the bottom 5 images that are shown here. These are the type of images that we are trying to find.
On the left, you'll see our model structure, which shows our images being processed through 2 convolutional layers, a max pooling layer, a dropout layer, a flatten layer, a dense layer, another dropout layer, and another dense layer. On the right, you can see the raw images were passed through the network, and the outcome was 2 buckets of images, whether they were classified as a transformer or not a transformer. For our hyperparameter tuning, we varied the batch size, number of filters in our convolutional layers, dropout rate, and learning rate. By storing the accuracy after each epoch was run, we were able to just run 30 epochs and determine at which point we saw the best results. On the right, you can see a local maximum in the validation accuracy at around 14 epochs, and again it hits the same value at around 28 epochs. We chose 14 epochs because that's when the trend of the validation accuracy rising starts to change and we see a little bit of toggling and wavering.
The final results of the model were tested against a test set of 1,175 images that had never been shown to the network at any point. The model was able to correctly identify 90.6% of all of those images, which is 1,064 of the test images. Of all of the test images, there were 44 that were transformer nameplates, and the model was able to correctly identify 42 of these, which represents 95.5% accuracy of all the transformer nameplates. What this essentially means is that because we have a low false negative percent and a high model accuracy, the model was able to correctly identify what are transformer nameplates, and it is an applicable tool to be able to use in industry to actually sort through the 10,000 different sites and the hundreds of thousands of images.
Thank you for your time. We hope this was informational, and if you have any other questions or would like to discuss further, please email us below. Again, I'm Bobby DeMarco.
And this is Matt Benbow. Thanks for listening.